Okay, a lot of us had problems with number one. You're gonna be furious when you see how it works. Okay, when 1 mole of methane is burned at constant pressure, 890 kilojoules of energy is released as heat. That means that methane has a heat of combustion of 890 kilojoules per mole. Well, you don't have a mole because CH4 has a molar mass of 16 grams. So, how many moles do you have if you only have 3.2 grams? And in 1 mole, there's 16. So, let's bust out our calculator. And we'll say 3.2 divided by 16 is 0.2 moles. So, if 890 kilojoules is given off when you burn 1 mole, how many kilojoules are given off when you burn 0.2 moles? So a little cross multiplication. 178 kilojoules are given off when we burn 3.2 grams. All right, that's all you do. It's easy peasy. Okay, let's do number 3. Oh, hang on, sorry about that. Okay, let's do number 3. Calculate the enthalpy of formation of propylene, C3H6, using enthalpies of formation and enthalpies of combustion. So we're trying to find how much energy is given off when we make this stuff. So what goes in to the formation of propylene? So you're going to need 3 carbons, and you're going to need 6 H's, but you can't have 6 H's because it's only H2, so you need 3 H2s. And we're trying to find this heat of formation. All right, we're solving by using enthalpies of formation and enthalpies of combustion. So let's get a combustion equation for this C3H6. And when we burn it, we're going to combine it with oxygen. Our products are going to be carbon dioxide and water. Let's balance this. And that will mean we need 9 halves of an O2. And according to this table, which is very handy, propylene has a heat of combustion of negative 2058. So we already know the delta HC, negative 2058 kilojoule per mole. Okay, what we're going to try to do is come up with some formation equations that will make this, just accounting-wise, equate to this delta HF. That's what we're looking for. So the first thing we want to do is flip this combustion equation around this guy so that the C3H6 lines up as a product. So let's flip this around. So what we're going to do is we're going to flip it around. We're going to say 3CO2 plus 3H2O yields 9 halves of an O2 and C3H6. That makes this a positive number. Now what we want to do is come up with a couple more equations that will account for our carbon and our H2, and we'll also eliminate the CO2 and the H2O from our step equations. That means that we want 3CO2 as a product, and to make 3CO2 you're going to need 3C and either 6 O's or 3O2 as it's written. After a while, you're just going to have all of these memorized, but we'll check out our table. And so for carbon dioxide, the heat of formation is negative 393.5. negative 393.5 kilojoules, but we're going to be multiplying this by 3. So negative 393.5 times 3 is now 1180. Negative 1180.5 kilojoules. Okay. Let's do the same thing for our water. We'll specify liquid water. Okay. And if you're wondering why we're specifying liquid water, look at the exhaust pipe of your car when the engine is running, and you will see liquid water being produced. And so we'll just use that. All right. And so we will make our final equation to produce 3 moles of H2O. And you'll do that by using 3 moles of H2 and 3 O's, which you can't have, so 3 halves of an O2. Okay. Because we specified liquid water, when we go up here to look, our liquid water is negative 285.8. Circle that from the last problem. Negative 285.8, but we're going to multiply this by 3. So that means, well, this is 857.4. It's a negative number. All right, let's double check to make sure that all of these line up. 3 carbons, 3 carbons, 3H2, 3H2, C3H6, C3H6. Everything else should cancel. 3 CO2 cancels, 3 H2O cancels, and if we rewrite 3 O's as 6 halves of an O2, that means we have 9 halves on this side and 9 halves on this side. It's just a bookkeeping method that these equations, all Hess's law is saying it doesn't matter how many steps we use as long as they are the equivalent of our target equation, and that's what we want. So let's take our 2058, we'll subtract from that our 1180.5, and from that our 857.4, and we get positive 20.1 kilojoules is the formation of propylene. Okay, last one. So many people were asking me about this one. Calculate the enthalpy of vaporization of water. You're going to be so furious. That means we're trying to come up with this equation, vaporization of water. What do? We've been doing this formation stuff. So let's see if we can find a heat of formation equation for both of these guys. And first off, let's see if the information is even available. Yeah, look. Heat of formation of water vapor, heat of formation of liquid water, negative 248 and negative 241.8, excuse me, and negative 285.8. So here we go. Let's write a formation equation for both of these. You want to make liquid water, huh? Yeah, well, you're going to need an H2 and you're going to need an O, or 1/2 of an O2. Delta HF is negative 285.8. You want to make water vapor, do ya? Yeah, well, smart guy. You're going to need an H2 and you're going to need 1/2 of an O2. According to the table, that's going to give off 241.8 kilojoules. Well, can we get these two step equations to equal this target equation? I think it is possible. Let's take one of these guys and flip it around so that liquid water is now a reactant. So we're going to flip this one, and now we have H2O, a liquid, which is going to bust up since we're running it backwards. And now this is positive. Well, H2O is a liquid. Boom. H2O is a gas. Boom. Everything else should cancel. H2, 1/2 of an O2, and that means that all we have to do is add this up. So we're going to say 285.8, which is a positive number, minus 241.8, which is a negative number, is 44 kilojoules. Now you might remember that way back in chapter 10, when we were calculating the heat of formation, vaporization of water, properties of water. You guys remember this? Where we already knew the delta HV for water, 40.79 kilojoules per mole. So this is something that we already have known. The numbers are a little different, but that's because we're getting these values from two different tables. I wouldn't worry about it. So you already knew this answer. You already knew that it took a little over 40 kilojoules to vaporize a mole of water. Yeah, well, you just found it. This guy right here. Mystery solved. All right, see you later.